Good morning. Welcome back. I hope you all had a good reading week break. And now I guess we're into basically the second half of the course. And what we're going to do is pick up where we left off. I'm not going to fully recap what we've done so far but in chapter 12, but we'll see a lot of it come up over the course of today. So what we're going to talk about now are implementing and tuning gradient boosting machines. So the last week and a half or so before the break, we talked about the basic, the conceptual idea behind boosting, and then the mathematical framework that underpins it, the idea of a gradient descent algorithm as a way of improving the performance. And now what we want to talk about is how, in some sense, to actually implement these as a machine learning algorithm. All right, so before we do that, let's make an important observation that we ended off with last time. So as previously noted, and we'll see this today in some sense, gradient boosting machines require extensive hyperparameter tuning. And to perform optimally. This does not mean that they can't perform well out, in some sense, off the shelf or out of the box. With a simple enough data set, their performance will be just fine. And in some cases, even with a more complicated data set, they still perform well without any tuning, just based on, in some sense, what the data looks like. We'll see this on homework assignment 3, which kind of gets assigned on Friday, and is on gradient boosting. That it uses a relatively simple data set called the iris data, and there you can perform, you can use a gradient boosting machine to predict the target variable, and it does a reasonably good job with relatively sort of default values. Anyway, so that's you'll see more of that in the assignment. So just generally, we made the following observation, which holds for most kinds of data sets. So random forest off the shelf, so to speak, meaning without any tuning, outperforms gradient boosting machines off the shelf. I'll just abbreviate that OTS. Okay. But tuned gradient boosting machines tend to outperform tuned random forests. And so just keep in mind, this is just a kind of general observation about how these algorithms work. It does not necessarily apply to every specific case. All right, and what we'll see last time, well, not last time, but when we talked about random forests, we did introduce the various hyperparameters that we can tune, and we talked about tuning the number of trees and tuning the mtry, so the number of features randomly selected during split-level randomization. That both of these were good approaches for tuning algorithm. But we didn't have to say much more than that. There were a couple of others we could look at that might contribute. In particular, we didn't have any particular tuning strategy in mind, which is what we'll see here with gradient boosting. The tuning process we need to be a little more careful about. Besides just the number of hyperparameters to tune, we have to think about the order in which we're doing things. So, okay, so before we actually get to tuning, let's talk about what the hyperparameters are. So there are two main types of hyperparameters, and in these types, we'll have different specific examples. We're called the boosting hyperparameters. So hyperparameters related to the boosting algorithm itself. And then under the assumption that we're working with decision trees as the base learner, tree specific. Okay. So as mentioned previously, our default assumption is that decision trees are the base learner. Now, you can, as mentioned previously, and we'll see this next class as well, use other base learners. This will change the hyperparameter tuning process a bit. If you use something really simple like linear regression as your base learner, then there's a lot less that you can do in terms of tuning. All right, so all of the terminology that we're going to use in the discussion will be in the case of decision trees, but I will mention here and there what would happen with some other base learner, or what, in many cases, what wouldn't happen because there's not really anything to do, right? Linear regression, you don't really have any hyperparameters to tune, so you would just, the tree-specific part would just disappear. Okay, well, first let's begin with the boosting hyperparameters. What do we mean by this? Oops, so fix that a bit better. Okay, so the first of these would be number of trees. One way to think about this is more generally number of iterations that you're going to run. So if it's not trees, if you're using something else, just how many times, how many steps are you going to go into the algorithm? Okay, so let's remember how this hyperparameter worked for random forests, okay, and see some of the differences. So recall that for random forests, tuning number of trees is important for error stabilization. But then remember, balanced against runtime. So there are always computational considerations. And in particular, for the random forest case, the computational consideration is important because there's not really any limit to how far you can go. Okay. So too many trees is for random forests is not an issue in terms of model performance. But it is for runtime, right? So if we keep adding more and more trees for a random forest, it's not going to hurt our model performance, but it's, of course, it's going to increase the runtime, and it may not be gaining us any advantage, right? And so that was the whole idea. Once we see that the error is somewhat stabilizing and we're not really getting any improvement, all we're doing at that point is costing ourselves computation time, and that's when it's kind of a good idea that, okay, that's probably where we should stop. Okay. So in particular, what does that mean for it doesn't affect model performance? Tree independence. So in the growing process, right, the trees don't depend on each other. And aggregation at the end, the way we aggregate them essentially by averaging, in the case of, say, regression. So tree independence and aggregation make it hard to overfit. Especially with random forests, once we've introduced the split level randomization so that we reduce the tree correlation problem, right? So that's where we might get some overfitting, but we deal with that in the random forest algorithm. Okay. But so the basic idea then is adding more trees is not going to cause us to overfit on those trees. Okay. But with GBMs, this is a problem. So gradient boosting machines can overfit on, say, too many trees. All right, well, obvious question then is why? What makes it, what's so different about this algorithm that we can actually overfit? Okay, so think about the regression case that we talked about a couple of weeks ago. We went through essentially what boosting regression trees is like. Okay, now something similar holds in the classification case, but it's a little harder to describe. So what happens in the regression case, why there, so in this case, this is because, well, think about how we boosted regression trees, right? The trees are trained in sequence. That was the idea of sequential training, but then sequential training, remember, was with respect to errors, right? So the trees are trained in sequence on the error residuals of the previous trees. Okay. Okay. So what was the idea there? It's in the sequential process, in the boosting process, we grow a decision tree, a shallow decision tree, and then we examine where sort of the biggest errors are. We look at the error residuals, and we train a decision tree, another tree on those residuals. So in other words, what we're trying to get is we're trying to have the algorithm learn from the biggest mistakes at the previous stage, and then then we combine those together to try and fix those mistakes as much as possible. Okay. So what's the result is, so the GBM algorithm will chase residuals in some sense. It will keep trying to fix the errors, okay, as much as you let it, for as long as you let it, for as long as allowed. Okay, so what's it doing then? It's in some sense, it's overtraining on the training data. So it's in some sense overlearning the training data. Overlearning here, I mean, really meaning overfitting, right? So it's kind of it's fixing the errors on the training data so that it fits the training data well. So thus it might not generalize well. Okay. All right, so that's a but in the sense of there's a problem here, right? If we use too many trees. Okay, so let me go scroll up here. So let's say this but number one, okay, because there's two buts here and they're kind of in opposition to each other. But number two, so here's another kind of a caveat. GBMs often require large numbers of trees. So often often thousands of them, as we'll see in an example, to perform well. To perform well predictably. And that's because the individual trees don't have much predictive power. Okay. So since each individual tree is shallow, in other words, a weak model. So then what we run into is kind of a problem that we have two competing effects going on here. The overall problem we run into is, okay, we need lots of trees. To perform well. But can easily overfit on too many. Okay, so what's the solution to this problem? Well, it's to be very careful about the tuning process. Something that we didn't have to worry so much about with random forest, where all we were looking for, we had a good rule of thumb for how many trees to start with. And remember, what was the rule of thumb for random forest? It was roughly start with 10p trees, where 10p was the number of features. And so that's usually not going to be too large, because most data sets don't have an enormous number of features in them. Okay. And that was often a good, that default was often pretty good, but maybe we go a little further than that. Here we have to be much more careful, and it might involve a lot more trees than just say 10p or anything close to that, as we'll see in our example. We'll go through the Ames example in a bit, and we'll make some comparisons with what happened in the random forest case as we do. Okay. So the solution then is tune the number of trees very carefully with k-fold cross-validation to find an optimal number. But we also got to be careful here with respect, in some sense, to the other hyperparameter values, because this can change. What's an optimal number for a certain set of hyperparameter values may change, be different than for another one. Okay, so we want to try to find an optimal number that minimizes the loss function on the testing data. All right, so already we see then that tuning the number of trees is going to be a little bit more difficult, more involved, and we need to think about it a bit more than with the random forest case. But now we've got lots of other hyperparameters to talk about in tune too. Right? So the other major boosting parameter, the one that's related to the boosting algorithm and not the specific trees we're growing, is the idea we introduced of learning rate. So we'll recap what this is in a second. Or the other name for this, remember, is shrinkage. Okay. So this is the parameter related to the gradient descent algorithm. So this controls how quickly the GBM algorithm learns. But more formally, so specifically, it controls the size of the steps the size of the iterative steps in the gradient descent algorithm, which is the mathematical optimization process built in. So the idea then is there's two general aspects to the boosting process. The number of trees, which can be thought of the number of iterations, how many times the process is going to iterate. And then the learning rate, in some sense, how quickly are we going to move in between those steps? How big are the iterative steps going to be from one to the next? Okay. So as a consequence of this, the learning rate, one way to think about what it's how it's going to affect the model predictions, also affects in some sense how much each individual tree contributes to the overall ensemble prediction. Okay. All right, and so the reasoning for this, why is there this relationship, is actually not too hard to see. Excuse me. So this is because there's a fairly clear causal link between the size, the learning rate, and the number of trees. So smaller learning rate requires more iterations to reach an optimum. So remember, what we're trying to do is minimize the loss function. We're trying to reach a global minimum for the loss function. And that means we're going to have more total trees, right? Every iteration is going to create a new tree. So more total trees required. Okay. And so then when we aggregate, so each individual tree in the aggregate contributes a bit less. Okay, so that's the generic idea behind what the learning rate is going to do to the gradient boosting machine algorithm, how it's going to affect it. Yeah, so what kind of value, how does this hyperparameter work in practice more specifically? Okay, so for the learning rate, or if you want shrinkage, so just as a reminder, the term shrinkage is often used as the name of the hyperparameter in R packages and so on. So the terms are synonymous. So if you see it show up, especially in any as a parameter in R, that's what it's referring to. So for the learning rate or shrinkage hyperparameter, the value range that it takes is 0 to 1, just the way it's kind of formally defined. But typical choices of it are on the lower end of this. Okay, so you might call typical choices, especially as starting ones. Because when we're tuning, we have to have some defaults in mind, or at least some starting values. We have to have somewhere to begin. Are approximately 0.001 to 0.3. So 0.3 is already in some sense a large kind of value for this, and so something like 0.01 seems relatively small, but this is actually pretty typical that you have fairly small values of the learning rate, but then you may, as you tune, you may increase them. Okay. All right, so within this range, what can we observe? So I'll make some observations about smaller values. Well, for larger values, it's all the same. I mean, you just flip everything around, right? So all the kind of the inverse commentary applies to larger values. So you can get there. So with smaller values, the model generalizes better. And it's easier to stop before overfitting. So 1 and 2 certainly are related to one another. Basically, the reason for 1 and 2 here, which are in some sense saying, a lot of them really saying this, a similar thing, is that if you're training the model with a smaller learning rate, you're not learning as quickly. The learning steps aren't as big, so you're not learning as quickly on the training data. So those are of course advantages. Maybe these is sort of a plus next to them, just as a positive. 3 and 4, on the other hand, in some sense, are disadvantages or things you have to watch out for. So a smaller value of the learning rate means you're going to have more computational complexity because you're not learning as much at every step. And longer run times as a result. And then if you've got a fixed number, if you fix the number of trees at this point, so the idea is that with a smaller value of the learning rate, every step is smaller. It gives you less information. It takes more steps to learn. Okay, so for a given number of trees, if you fix this, well, if the learning rate is too small, there may not be enough steps provided to optimize. So for a given number of trees, you get an increased risk of not actually reaching a global optimum in the gradient descent algorithm. Okay, so those are disadvantages. So let me put a minus next to them. So they're negatives. Okay, so that's what I mean by the plus and minus here. Positive and negative, kind of positive aspects and negative aspects. So if you use larger values of learning rate, this all flips around. Okay, so then a larger value of learning rate makes it more likely you'll overfit. In other words, the model won't generalize, but also it will decrease the runtime because the steps are bigger, so it takes less steps, and it makes it more likely you do reach the global optimum. So it's in some sense, you're balancing out as usual like overfitting against performance against runtime. All these kind of factors keep coming into play. Like we said, all the fundamental stuff shows up all the time. So just keep that in mind. All right. So those are the parameters for the boosting algorithm. The second broad group, where there's lots of additional ones to say, are the tree-based hyperparameters. Now we've seen lots of these before, but we won't necessarily go through the definitions of all of them that carefully. But we will talk about how to implement them, and in particular, we'll see differences compared to, say, in the random forest case. All right, well, the first hyperparameter, a tree-based hyperparameter that we've seen before, is depth, right? The maximum depth of the tree. Okay. So I won't redefine what depth is, but let's talk about it in the context of gradient boosting. So for gradient boosting, trees are shallow. And shallow is going to mean 1 to 8 splits, roughly. Let's consider smaller, so closer to 1. So 1 would be a decision stump, and that's actually often fairly common to use. Well, let's say maybe like 1 to 3 splits. Well, now you're going to need more trees. because each tree is a correspondingly weaker model. Than if you used a few more splits. But you have more, what you might say, called per tree computational efficiency. Because now, if you only have a few splits, every individual tree does not take that long to grow. Okay? There's not much to compute. If you go on the larger end of a shallow tree, or closer to, say, 8 splits, well, now you're more likely to overfit because the tree is getting into kind of the deeper end of what you might use in this algorithm. But on the other hand, you can capture more subtle interactions between the features, right? So you get more structure. And for a very complicated data set with lots of features, this may be desirable. You might want to see how the different features are interacting at a deeper level than you would just get with, say, 1 or 2 splits. Okay, so that's one thing to think about in general when it comes to the depth. Now remember, there's other ways to control that are helpful for controlling depth, such as minimum node size. So typically for gradient boosting machines, we want to have a decently high minimum node size. So this will help control the depth of the algorithm. So typically 5 to 15. But the trees already have small depth. So this hyperparameter tends to not matter so much other than for small data sets. So if you don't have many data observations, you want to make sure, if you have a small data set, your nodes could get small very easily, even if it's only like a small number of splits. Okay. So other than for small data sets, but since the trees have shallow depth. So the basic idea is that with gradient boosting machines, we explicitly make sure that the depth of the trees is small so that they're shallow, and then the minimum node size won't tend to matter. But if you have a small data set, then it could matter still. So it's just something to keep in mind there. So a higher value of minimum node size is you'll avoid overfitting even more, right? A value on the lower end here can be helpful generically for classification problems with unbalanced classes. Remember that unbalanced classes means that you've got classes, you have categorical variables where some of them have lots of values and others don't have very many. And so why is that? Why does that matter? Like in the sense of why is a lower value of minimum node size helpful there? Because in some sense, if you have too many observations at a single node, and then you're looking at, say, you're classifying on categorical variables, you're just splitting on them. The ones where there are relatively few values are often going to dominate over the ones where there are lots of values. Because you may, for instance, if you've got a categorical variable that has a lot of values to it, maybe if you have a lot of values at your node, they're all kind of all over the place in that variable, but then some other categorical variable, you'll have a clear majority or at least a plurality. So you kind of run into this situation where if the nodes are too big, you're not going to get information on some of the variables. Okay, so it's hard to say specifically, but it's just one of those things you can run into. So just worth keeping in mind. All right, so that's kind of the summary of some of the main hyperparameters. Now let's talk about implementing in R. Also, we haven't talked yet at all about stochastic hyperparameters. So those, if we want to do stochastic gradient boosting, which we introduced previously, there's additional hyperparameters, and we'll get to that a little bit later. Okay, the standard way of implementing a typical gradient boosting machine in R is the package called GBM. Okay. So GBM has many options. Here are some of them. Formula. So this is the base model to fit. Distribution. So this is actually the name for the loss functions, how to measure the loss. Data, well, this is simply the data set to use. N dot trees. As the name suggests, this is the number of trees. Shrinkage, well, that's self-evident. So remember that that's just the name for the learning rate. Interaction dot depth. This is the max tree depth. N dot min obs in node. As the name suggests, this is the minimum node size. And CV.folds. This is the K in K-fold cross-validation. So you can set how many folds to use for cross-validating. Okay, so there's lots of options then to consider. And then here's our tuning strategy. Okay. So this is where, in some sense, there's a big difference with random forests, where we said, just to kind of keep reiterating, random forests tend to perform well off the shelf, so with minimal or no hyperparameter tuning. But also, when we talked about tuning random forest hyperparameters, it's worth keeping in mind, we didn't really specify a particular sort of strategy or step process, right? We talked about what each hyperparameter did, but we didn't really say, okay, you need to tune this one, and then if you tune the other one, you've got to go back and look at a previous one and how they interact. Here, that's a lot more important. Okay. So we're actually going to have sort of a step process to kind of go through. Okay, so step number one is to choose what we might call a relatively large learning rate. Okay, what does relatively large mean in this context? Something in the range of 0.05 to 0.2. Okay. So you really see here that if that's kind of what we call relatively large, that learning rate values tend to be pretty on the small side of the parameter range. So we start by just picking the learning rate somewhere in there. 0.05 is a very common starting one. Then we tune the optimal number of trees. For this learning rate. So let me actually just add, so just to be clear, so 0.05 is common. 0.1 is as well, just kind of values like that, but something in that range. And then we tune the optimal number of trees for the starting one. Okay, so then we fix this. So fix this value for number of trees. And then essentially what we try to do is tune learning rate for that against that fixed value. Okay. Tune learning rate on this value. And assess, at this point, performance versus runtime. So in other words, what you're going to do here typically is after you're going to fix a number of trees at step 3 here. You're going to run a grid search over various values of the learning rate, and you're going to look at, okay, how is performance interacting with runtime? Each model run, are we gaining any performance gains, or is it taking longer? So for instance, if they're all roughly the same amount of time, right, the runtime is basically flat across them all, then you might look for whatever one gives the best performance. Okay. All right, so then, based on your and there's of course a little bit of subjectivity here, right? So you're looking at runtime versus performance, and you've got to think about kind of where you want that balance to be. Okay. So you choose a learning rate from step 3. And then tune tree-specific parameters. So depth and node size. Now you fix the tree-specific values obtained at step 4. And then we look at tuning learning rate again. So try lowering learning rate. So remember that decreasing the learning rate from a particular point is going to increase typically the runtime, because the steps take longer, but could improve model performance. Okay? So lower the learning rate and assess any possible improvements, because you don't necessarily get any. Okay. In performance versus runtime. Okay. All right. That's step 6, and we set what we might call final, because they're not actually final, but final for the moment. So clean that up a bit. So set final hyperparameter values. Writing's not good today. From steps 1 to 5. And use k-fold cross-validation, for more robust error estimates. Or use k-fold cross-validation as you go in steps 1 through 5. And omit step 6. Try to make that look a little cleaner. Okay. All right. So that probably sounds like a pretty complicated process. But let's see kind of how you would actually implement it, and let's work through the Ames example and see what kind of improvements we get through the hyperparameter tuning process. Okay. So our starting point, so in other words, what if we use just defaults? Well, we start with the root mean square error of approximately 24,600, which is already pretty good. But let's see then the improvements we get by working through the tuning process, and also where we don't actually get any improvements. Okay, so suppose we do steps 1 through 2. So then what we'll find is that the number of trees is going to be the optimal number of trees for kind of a default learning rate is going to be approximately 1,200. Notice that that's quite a bit larger than, say, the 750 or so that we needed for error stabilization in the random forest case. Okay. But we do get a reduction in root mean square error by tuning the number of trees and ending up with a larger value. We end up with about 23,200 as our root mean square error. So at step 3 now, remember we fix the number of trees and we assess various values of learning rates. Okay. So we grid search on learning rates across the 0.005 to 0.3 range. Okay. And this takes approximately 10 minutes. Okay. So this is with whatever kind of computing setup the textbook has, which is I think is actually pretty similar to mine because I've repeated some of this and it takes about the same amount of time. Okay, so if you run this grid search, and this is following kind of, but in the way the textbook has it set up, what you'll find from the grid search is that you end up with a learning rate, an optimal learning rate of 0.05. The number of trees at this point after grid searching and using k-fold cross-validation has increased to 2,375. And the root mean square error now has reduced to approximately 21,400. Also remember that when we're doing this grid search at this step, we were trying to assess performance versus runtime. Okay, so if any particular values of the learning rate give you much better runtime, then you might want to consider that. But in this case, you'll see that all models took approximately 2 minutes to train. So there wasn't any particularly big difference between various values of the learning rate and the resulting runtime. Okay, so we found 0.05 ends up being relative, kind of an optimal value for the learning rate. So then we'll set the shrinkage, so learning rate to equal 0.05. and now tune the tree parameters. So depth and minimum node size using a grid search. Now, in this case, we're going to end up grid searching against, so now we actually have, in some sense, a two-dimensional grid, right? Because we have two hyperparameters, depth and minimum node size, and what we're going to do is assess all possible combinations of those across the grid. As a result, this grid search takes a little while. It takes about 30 minutes. The end result, and also, again, we're cross-validating as we go. And so the number of trees is sort of being tuned as this happens. So what we end up with after this is that n trees, the number of trees is 4,000. The depth, the max depth is 5, and then the minimum node size is also 5. And with those values, the root mean square error, the best cross-validated root mean square error is about 20,700. Okay. So that's actually pretty good. So think about where we started from. We started from root mean square error about 24,600 with defaults. And by tuning, now we, of course, took some computation time, but we reduced our mean square error by about 20,700, which is a pretty good percentage reduction in error if you think about it. The decrease as a percent of the original error is fairly large. So that's a good kind of just way to see that tuning in a gradient descent algorithm or a gradient boosting algorithm can really have a good effect on the loss function. So there can be a substantial improvement. Okay, so step 5 now, we're going to fix these. So we would set interaction.depth, the maximum depth, to be 5. And then the minimum node size, n.obs, so min obs in node, to be 5. And then we want to see what happens if we increase the number of trees and then try various values, small values of the learning rate, right? So we increase the number of trees to a large number so that we have sufficiently many trees. And then we test out, essentially, we assess small values of learning rate. So lowering the learning rate, what happens? Okay. So now increase n trees. To 8,000. Reduce learning rate to various smaller values. So try out different values of the learning rate that are smaller than the one we had fixed. Remember that our previous one was 0.05. So maybe say 0.01 to 0.05 range. Try out values in that range. So, but the result is actually that we don't get, it doesn't really help. So there's no improvement. In root mean square error over what we had before. In root mean square error over what we got at step 4. But runtime increases, well, which makes sense because we're using a smaller learning rate, so it takes longer, to approximately 6 minutes for the best performing models. Okay, so that's kind of an indication that we didn't really gain anything here, but also it takes longer. So, so the conclusion, in some sense, is that values at step 4 and resulting root mean square error seem to be optimal, at least for how we've trained it and tuned it. Okay. That root mean square error that we obtained at step 4, 20,700 for the Ames housing example, is considerably lower than what we've obtained in any kind of previous model that we've used. If you go back and look at our discussion of this example, when we've used KNN, we mentioned Mars, even though we didn't talk about it. We've used a single decision tree, a single prune tree that wasn't a very good model. And we've seen how to train a random forest on it. So this is the best result we've got so far. So a good indication that a tuned gradient boosting machine can be a very powerful predictive model. All right, so the next thing we can do is add in the stochastic idea. Okay. So the idea here is we take our regular gradient boosting machines and we move to stochastic gradient boosting machines. And what's going on here is we're adding in randomness. Okay. So why are we going to do this? So we're adding in randomness, and how we're going to do it is through subsamples. So in some sense then, going from gradient boosting machines to stochastic gradient boosting machines has a lot of kind of similarity with going from bagging to random forest, where we added in randomness by subsampling on features. Okay. So why is this a useful thing to do here? Well, we discussed this last time before the break. So this, in some sense, disrupts the structure for sort of complex loss functions, ones that have a lot of they're very complicated structure. And helps avoid we describe it as sort of getting stuck. At a non-optimal point in the gradient descent algorithm. She's going. Okay. So the idea was that if you have some complicated loss function, it could have many local extrema. It could have sort of plateaus in other areas and saddle points and places where the gradient is either close to zero or not behaving kind of in a very predictable way. And so you try to avoid that. Okay. It also, because what we end up doing is subsampling, right? So we're not using the full, say, training data all the time. It also makes the algorithm faster because there's less to compute. So even if the loss function kind of problem doesn't seem like it's going to be there, it may be advantageous to do this just for computational considerations. Okay, so what are the stochastic hyperparameters? So the idea is we have all the same parameters as before, so we haven't lost anything from the gradient boosting algorithm. we want to introduce hyperparameters now that will induce the randomness that we're describing in some way or another. Okay. There are three approaches. So there are three main stochastic gradient boosting machine variants. Okay. So one is to subsample, so rows, by which we mean the data points, right? Data observations. Before growing each tree. So the idea is at step one, or approach one, is we're going to, when we train each tree, we're only going to train it on a subsample of the training data, okay? Some random sample of the training data. The second approach is to subsample columns, so features, before growing each tree. So the idea here would be when we grow the tree, we only look at a certain subset of the features for the splits. And the third is essentially the kind of idea in the split level randomization in random forests, is subsample columns so features, before considering each split. Okay, so the difference between 2 and 3 then is in approach 2, for each tree we're only going to consider a subset of the features, but then for every split we'll evaluate all the features that we're considering. Step 3 or approach 3 is saying, well, for every split we're going to randomly sample on the features, so we're going to do split level randomization. Okay. So what are the things that we can say about these three approaches? Can we make some general comments on them? So for approach 1, so typical here, remember what we're sampling is we're going to subsample training data. So typically the way we're going to do that is we're going to set some percentage of the training data and tell the algorithm to randomly select that. So typical here is 50 to 80% of the rows, right? So of the training data for each tree. Okay. So what we might call aggressive subsampling, to introduce a lot of randomness, so under 50%, so subsampling, can be beneficial. It can be explored whether this is actually useful or not with k-fold cross validation. Now, approaches 2 and 3 are fairly similar, and as mentioned, they are similar as hyperparameters to mtry, right? So these are similar to mtry for random force with similar considerations. So in other words, what do I mean by similar considerations? Well, what percentage of the features do you want to sample? Okay, so there were kind of two. So what were those and what were the driving factors between those considerations? So remember that if we have noisy data corresponding to few relevant features, what do we do in this case? Sample a higher proportion of features for a better, for more likelihood of selecting relevant ones. Okay. On the other hand, if we have lots of relevant and correlated features, here you typically choose a lower percentage. So sample a lower proportion of features to introduce more randomness. You'd have essentially a similar kind of problem to tree correlation, right? Where the same splits are showing up over and over again in the trees, and so you might want to avoid that. Now, how do you actually implement this? Well, you can do it during the tuning process or at the end. Okay. So going from gradient boosting to stochastic, can be implemented during or after the previously discussed hyperparameter tuning process. Okay, so specifically, so introduce it during step 4, when tuning tree-specific parameters. Because if you think about it, these stochastic parameters, they are tree-specific, right? They're about how much of the data are we going to choose when training each tree or each model-specific at least, even if it's not trees, or how many of the features to consider for the splits. That's tree-specific, right? It's not related specifically to the boosting algorithm itself. It's not about the number of iterations or the learning rate. So you can do it when you're tuning the tree-specific parameters. You could also do it after step 6 with the optimal base model already chosen. Optimal, what we call basic GBM model. So if you do it after step 6, the basic idea here is you're just going to consider, okay, does adding in this additional randomness actually improve over what we already have? Okay. So stochastic gradient boosting machines can be significant improvements over basic ones. For some data sets, this is possible, but not always. Okay, so the stochastic element doesn't always really help because, well, in some cases, the loss function isn't that complex. The structure is not, and in particular, the way it interacts with the data, there's nothing weird going on. And so it won't actually do much. And then the runtime improvements might not matter much either. Okay. So an example, well, let's use the example we've been talking about. So the Ames data sees essentially no improvement. From stochastic gradient boosting over the basic one that we already talked about. But it is, in general, something that should be considered. The additional randomness may help with various issues involving the loss function and involving, say, tree correlation and so on, and it may speed up the algorithm because of decreased runtimes. All right, so that's the end of today's discussion for tuning gradient boosting machines. What we'll see on Thursday to wrap up Chapter 12 is what happens if we kind of go to a more advanced version of the gradient boosting algorithm with even more options and features available to us, specifically what's called XGBoost, extreme gradient boosting. And do we get improvements from that? It's a powerful package in R that in some cases may actually add a value by increasing the model performance. So that will be what we'll talk about on Thursday.